Hello class, and welcome to the lecture on terrain analysis. I think you're going to find that this is going to be one of the more fun topics that we discuss in this course, as there's a lot of really cool things that you can do with the data and the tools that we're about to discuss. So by the end of this week, you're going to know where to find elevation data. You're going to learn how to derive other data sets from that, such as contours, slope, aspect, hillshade, viewshed, and so forth. So there's a lot of data sets that can be gleaned just by understanding a few basic concepts in terms of elevation. So before we get started looking at digital elevation models, I want to talk a little bit about a recent landslide that we had here in the United States. I believe it was back in like spring 2014, if I remember correctly. And for those of you that might remember, Oso, Washington had a landslide. This area here, you can see where the slope failed. And if you remember, all that mud and so forth actually overtook a town and altered the river channel that was going through here, and unfortunately a lot of people lost their lives as a result of this landslide. So I'm just going to quickly show you what this might look like using digital elevation models. So going here and popping back up to this data frame. This is the area where that landslide happened, where I have the dot there with my coordinates is where it is. And just by looking at this, what's called a painted relief, you can get a sense of the elevation of this area. And if we look over here in our table of contents, we can see that with this digital elevation model that we're looking at, the lowest elevation was 225 feet and the highest was 937. And it's very easy to pick out where the steep slopes are by looking at this digital elevation model. What we can do that's kind of cool is we can actually also look at this in a product that's called ArcScene, which allows us to look at it in 3D. I'm just going to quickly open that as well. The product that I'm about to show you is actually one that we're going to start using next week, when you're going to learn how to render landscapes and so forth in 3D. Not only can you just render landscapes in 3D, you can do other 3D analysis type of functions in ArcScene, but we're going to concentrate mostly on the terrain and landscape aspect of ArcScene. So here's the view of Oso in 3D. You can actually kind of move your terrain around a bit. And when we look at things in ArcScene with the 3D aspect applied to it, we can really start understanding, why a landslide might have happened there. When we looked at it in ArcGIS, you still get the sense that there's some, steep slopes there, but it becomes even more apparent in this product. And then you can kind of see, why that happened. And for those of you that might remember, when this landslide happened in 2014, this area of Washington was receiving an uncharacteristic amount of rain, which caused the soil in the slope to be so heavy that it essentially was just like an avalanche in coming down. So it was not the first time that a landslide happened in this area. Obviously, you can kind of see even old landslide scars. So this product allowed researchers to study the landslide a little bit more and even quantify the amount of sediment that might have been moved in that particular incident. So this is just one application of the data that we're going to be using today, is looking at natural disasters and so forth. So we're going to be talking about terrain analysis, and essentially what this is, it's looking at how natural and man-made features of the terrain combine with other relevant factors to predict the effect of terrain. So some types of terrain analysis are where to plant crops based on certain aspects. For instance, for the winery owners and vineyard owners, grapes tend to favor southeast facing slopes. So what you can do is pick out all of those slopes in the GIS software to see which slopes face that direction, so that you have a better idea of where to plant crops. And essentially, just like we've been doing with the site selection in past weeks, like you have all these criteria, like grapes, for instance, have a certain soil type that they thrive in, they have certain aspects that they thrive in, a certain amount of sunshine, and you can actually model all of that and find the most favorable locations for planting that specific crop. Terrain analysis is also used to figure out where to position soldiers. And I know a lot of you, or some of you in the class, have former military experience, but essentially it can be used to figure out what are the best locations to position soldiers so that they have the high ground and so forth. Terrain analysis is also used to predict historical settlements. Throughout history, it has been found that there are certain criteria where civilizations thrived and where they popped up. They're close to a source of water. They have specific elevations. They have a specific criteria that allow them to be successful. And then, like I talked about, you can use terrain analysis to predict different types of hazards in Pennsylvania landslides, and in the example I showed you, landslides. So we're going to start working with elevation data today, and we're going to see different forms of it, but most of the time when we are working with elevation data, we're going to be working with something that's called a digital elevation model, or DEM, and some people call it DEMS. I prefer DEM. So you'll probably have seen that acronym if you've been kind of just trolling around PASDA a bit. You might have come across that and kind of wondered what it is. So probably the first form of elevation data that we're all somewhat familiar with, if not very familiar with, are topographic maps. I imagine that all of you have seen a topographic map at some point in your life. But essentially, the type of information that's on a topographic map is showing you, you can see that all the brown lines are the contours, and the closer the contours are to one another, the steeper that area is. The further apart the contours are, the flatter that particular area is. And it also has just some general reference features on there, like roads, cities, and so forth. And these are used for a lot of different purposes, for navigation, for hiking, for, that type of thing. So essentially, the whole point of a topographic map is to be a depiction of the terrain that you will be navigating. But a form that we can work with in a GIS that is a little bit more powerful than a topographic map is what's called a digital elevation model. The problem with these topo maps is that they're a static picture of elevation. You can't do anything with this other than using it as a visualization. And not to say that you can't derive lots of different things from here, like you can derive how far things are apart and so forth, but it's not as interactive as what a digital elevation model can be for us. So there are a lot of different digital elevation models out there, and the digital elevation models all have different resolutions to them. The first and probably the most major program to capture digital elevation models was done by the US Geological Survey, or the USGS. They have 10 meter by 10 meter DEMs available for the coterminous United States. So it's a nationwide coverage, which is really cool, because not every time that you do a GIS project is it going to be in Pennsylvania. It might be elsewhere, especially if you're working for a GIS company that takes projects all over the world. These are might be a little bit more applicable to what you're doing. But the state of Pennsylvania, back in between 2006 and 2008, used LIDAR, which is a remote sensing technology, to collect elevation data for the whole state of Pennsylvania. And from that LIDAR data that they collected, they processed DEMs from that are 1 meter by 1 meter in resolution. And these are available for the whole state of Pennsylvania. Now, I want to show you two things here. The first is a DEM comparison of the 10 meter versus the 1 meter. So you can see that there is actually a really big difference in terms of what you're looking at. So This little square that you see here is a PA map DEM, one from Pennsylvania. And you can see, just kind of briefly notice the amount of detail that you see on this. If I turn that off, underneath it is the USGS DEM. And notice when I turn that off, how different the resolution is than what we see over top of it. It's pretty substantial in terms of what you can pick out, because on here you can pick out like roads, you can pick out different geographic features a little bit easier. But if we take that away, notice that that all goes away on the 10 meter by 10 meter. So it's really nice to have something that has this quality. Now, I mentioned that Pennsylvania did this data collection project between 2006 and 2008 to collect high-resolution elevation data for the state of Pennsylvania. Other states have similar initiatives, but there's no one standard data collection project for digital elevation models. It varies state by state and region by region. So you're not always going to have something to this degree for other states. It might be better, it might be worse. It's it is highly variable. So that's the first thing that I want to mention about USGS versus PA map DEMs. The other thing I want to mention is where the heck do you even find them? You've been on POSDA before, and we've looked at this area of data shortcuts before. The digital elevation models are located under elevation and topos, and the PA map DEMs that we're going to be using is this link right here that says PA map program 3.2 foot digital elevation models. 3.2 feet is equal to 1 meter, so that's the resolution. And then this is where you would go to download them. We will get into at some point how to figure out what DEM that you need for your particular area of study. But what you're going to find when you actually look at this is that there's a ridiculous amount of digital elevation models available. Even going through every one of these directories has DEMs in it, so you can see all of these that are listed there. And just excuse me 1 minute while I'll go get my light back on. The USGS DEMs are also found in that same area. If we scroll down, we see Pennsylvania Digital Elevation Model 10 meter USGS, and that's where we would go to download them. There's also 30 meter resolution, but why would you use 30 meter when you can use 10, and why would you use 10 if you can have 1? So you usually want the best resolution for what you're doing, unless for whatever reason resolution isn't that important to you. Now, going back again, I just kind of want to show you something that might be a little overwhelming. I'm going to add a data frame, and I'm going to add a couple of different data sets to this. ARC is being its usual slow self, as you can see. I'm going to add just a shapefile of the state of Pennsylvania for geographic reference. And then I'm going to add 3 different data sets to this. The first one I'm going to add is the USGS Quadrangle Index. So I'm going to hit my Add Data, go up a level, go to my indexes, and there we go. And I'm going to hollow that sucker out. So this indexing system that you see here is each one of these squares or rectangles is a quadrangle. And let's say your study area is in this quadrangle here. To figure out which one that you would have to download from POSDA, you would just simply click on that quadrangle, and it tells us that that's the Indian Town Gap quadrangle. So when we're in POSDA looking for that particular data set, you can see all the quadrangles in Pennsylvania are listed here. The way that you would know which one you need is essentially just overlaying the index here in ArcGIS. Even if, like, let's say, let me add one other data set here. I'm going to add we worked with Memorial Lake, I believe, earlier this semester. I'm going to add that to this. Notice that Memorial Lake is right there. So if you are trying to figure out, let's say you have a shapefile of your study area, add that shapefile to your map, and wherever that intersects the quadrangle, you know that's the one that you have to download. So like if now maybe I'll add a Pinchot to it. Notice that that's located down here, and you also notice that it actually crosses into two. So to figure out which one that we would need to download, we just identify them using our identify tool on our tools toolbar, and we see that Dover is one of the names and Wellsville is one of the names. So we would again just go to POSDA and find those and download those. So that's how you would find the ones that you need for the USGS DEMs. And this index that you see here is available for download on POSDA so that you can just kind of keep it. And that's actually something I keep with, I never get rid of it because it's something that I always used to figure out which DEM I need for a particular study area. So let's turn those off for a second. Now let's add the indexes for the PA Map project. And these are really gonna be quite interesting. So we have a north index and a south index. So see all these little squares here, the crazy amount that you see. And again, I'm going to quickly just make these hollow so we can see through the whole state of Pennsylvania. Every single one of these little squares is a DEM. So if we want to identify the DEM that we need, we just simply hit the Identify tool, click on it, and it gives us a number. So then when we go back to this area here, we have to find that number in this area here. So it can be a little bit overwhelming in terms of actually identifying and finding the one that you need. Now, what you would do here is, you know, identify the ones that you need, and then there is a graphic available that tells you which year each county was flown, and then that would help you identify which year to go to here. And when I clicked on this one, the number began with a 4 that we identified. When you're in this area here, when you have to go to which directory, you pick it, the one that the one that you identified begins with. So ours began with 4, so we pick this directory, and then we would find it in that particular directory. We're not going to be finding DEMs this semester. I'm going to provide them to you, and so you know how to use them. But I just want to let you know that they're actually, this is where they're located if you ever do want to use them. For those of you that will be going to the upper level courses, we will be using these extensively, particularly in the remote sensing class, and then also in cartography, so that you will see these again, and we'll go through this in much more thorough detail at that time. But I just wanted to give you an idea of where all this data comes from and how you would get your hands on it had you wanted to. Now, going back to this for just one last second, and then I'll get back on track here. Notice all these squares, and this is kind of fun. So if we look at our attribute table for the North Index, there are about 6,700 different DEMs in the North Zone, and if we look at the South Zone, there's about, again, 6,700 or 6,800 different little squares. So add those up, there's well over 13,000 digital elevation model files for the state of Pennsylvania. So it's pretty crazy, the amount of data that's there. So as I mentioned, you know, there's the two types of digital elevation models that we'll be working with. For your assignment, we're going to be working with the PA map ones, the ones that have a little bit more resolution to them. Now, just some definitions before we proceed with working with digital elevation models. One of the digital elevation models are the starting point for terrain analysis. It allows you to do a lot of different types of modeling, and it's the starting point. So from a DEM, you can create a sloped data set, which tells you how steep or how flat something an area is. So you're going to learn how to generate slope data sets. You're also going to learn how to generate aspect data sets, which show the direction of the slope. You're going to learn how to do hillshades, which is my favorite because they're really cool looking, which essentially is like a relief map. And I'm going to show you how to do a shaded relief because I think they are a little bit more valuable than just a regular hillshade. And then the really awesome thing is that you can actually generate contours based on your specified interval for analysis. So I could generate a 2 foot contour if I wish. I can generate a 10, I can generate a 50. It really is you know, up to you what you want that contour interval to be. So you can see kind of some of the different types of data sets that you can generate from there. And on this, it gives you some surface analysis applications for each of the different applications that we're going to be learning. We're not going to do cut fill in this class, but that's actually really cool because you can look at volumetric change and how much sediment has been removed. This is something I actually did in my thesis research in grad school. I was quantifying how much sediment was either removed or added to the beach environment due to a coastal storm, and that cut fill tool was really, I just used that constantly. You can also calculate view shed. So if let's say that you're standing on the top of Hawk Mountain and you want to see what is visible from where you're standing. This allows you to see what is visible and what is not visible, which is kind of cool. And again, unfortunately, we're not going to be doing that in this class, but you're going to find that once I show you how to do these, you're going to be able to easily figure out how to do some of these other ones because they are pretty intuitive. So I'm going to just start in here and kind of show you around a bit with a DEM. And let me go back to this. Actually, I lie, I'm gonna do something else. I'm gonna add a digital elevation model for Johnstown, Pennsylvania. And for those of you that are familiar with Johnstown, you will know that back in, I believe it was 1892, they had a big flood. The dam failed and a lot of people were killed there. This is the digital elevation model of the Johnstown area. And when it's first added, it looks a bit like an X-ray, is how I always kind of describe it. What's really cool with this is over here, this shows us the elevation range of all the elevation values within this particular digital elevation model. So the lowest value is about 1,481 feet, and the highest value is about 2080 feet. And you might be wondering, well, how the heck do we know what units this is in? If you want to know what units your data is in, you can go to your source tab, and in here it will tell you your units. And that's really important to check because it's not always feet. A lot of digital elevation models that you'll download, for instance, the USGS ones are in meters, and it's important for you to know that so that you're actually communicating the information correctly. So this is in feet. What's also neat we're going to just zoom in really tight here. And maybe let's try to do a place that has a little bit more distinction. Let's say right here. Notice how as you zoom in, you can kind of see all the pixels and you can see the pixel boundaries, and hopefully you can see that a bit. When we use our identify tool to click on any one of these pixels, it will give us the elevation value at that particular pixel. So as we click around, you can see the elevation value. So every 1 meter by 1 meter pixel on here has that elevation value assigned to it, which is how we're able to do so many things with this data set, is because of that the fact that it has a elevation value assigned to every single pixel. Zooming out again, this doesn't really tell us too much as it is rendered. Essentially what it's telling us is that the blacker areas are the lower elevation values and the whiter areas are the higher elevation values. So there's actually symbology that can be applied to this to make it look a little bit more elevation-y. And if we double click on our data set and go into our layer properties, we have our symbology tab, which you should be really used to using at this point because we made graduated color maps, we made unique value maps, and all sorts of things. And then here you have a color ramp, and you can see that this color ramp progresses from black to white. What's really neat is if you right click on your color ramp here and select this option called graphic view, it will change it from the color scheme to the name of the color scheme, which is really important because when we click down on this, then you can see that it tells you what the color schemes are appropriate for symbolizing. So essentially these are some of the conventions in terms of symbolizing different data sets. You can see that there's 2 color schemes for elevation, and if we scroll down a little bit more, we're going to be getting to slope shortly. There's one for a surface here, which you can actually use that if you wish. It's not my favorite. You can see we're going to get to aspect. There's one for aspect. So there are predefined color schemes, so don't fight them and pick your own. I mean, in the upper level courses, specifically in cartography, we learn how to create our own color schemes for our data, but again, you base the selections that you're building that color scheme for based on convention. So I'm going to select this one, and you can kind of see what that looks like. The bluer areas are obviously where the border is, and like the white areas are the higher elevation areas. So this is one of the color schemes that's appropriate for symbolizing elevation data. So before I go on and into the tools that we're going to be using, I want to expose you to a window that's available in ArcGIS, and this was actually new as of version 10.0 in ArcGIS. So this was actually something really exciting when it was added because it made working with imagery, a lot easier and quicker, and really has saved a lot of headaches. So if we go to our Windows tab and then go to Image Analysis, it brings up what's called the Image Analysis window, and I like to dock mine over here on the side just so that it becomes a tab, just like some of your other ones. But if we will see all of our data that's an image from our table of contents here. Notice that everything is grayed out. If we want to activate some of the tools, we have to actually click on our DEM, and then it will tell us what tools we're allowed to apply to this particular data set. So it's actually really smart because it's not letting us use certain things that don't apply to the data set, so it doesn't have you apply invalid tools. One of the neatest tools that's available here is what's called a shaded relief option, and it's this button here. It applies a color scheme to our shaded relief, and it creates a nice little relief map. So how awesome is that? This allows us to create what's called a painted relief. Now, anything that's generated in your image analysis window is considered a temporary file. This has not been saved anywhere on your hard drive. So if you would close out of this, this would go away. So if you want to keep this as a permanent data set, you would have to go to Data, Export Data, and export this as a file. And I'm actually going to skip that for now, but just know that these are temporary files unless you make them permanent. You can also go over here, just select the one that you want here and hit save, and that will also take you to that very same window. So that's one of the really cool tools that we have in the image analysis window. And I'm going to go over here and shut that off, and I'm going to get rid of my image analysis window for a second. Now, we are going to about to generate a number of data sets. In order to do so, and this is something that gets a lot of people in the assignment, is that you have to turn on your extensions in order to be able to use these tools. When you install the software, I'm not sure if you remember, but you also were asked to install all the extensions, and the ones that we work with when we work with digital elevation models are the 3D analyst one and the spatial analyst one. You don't have to turn them on, both of them on, though I do. I actually just keep everything on all the time normally. But to be able to use the tools that we're about to go through, you have to select 3D analyst and spatial analyst and then hit close. So I'm going to go over to Arc Toolbox. And wait for it to expand out. Okay, there we go. And if we, let me just kind of collapse everything. If we look at our 3D analyst tools, we have one that's called raster surface. If we hit the plus sign next to that, we see all of our surface tools here. The first one that I'm going to generate is going to be a contour data set. And when we generate a contour data set, this is going to create a shapefile. So kind of make note of that, because when we work with all this data, some of it is going to be shapefiles and some of it is going to be image files, similar to like the file extension for an aerial photo. So for this, our input would be our digital elevation model. Then we have to tell it where we want to save it, and again, make sure that you are proactive in this and that you're putting it in a place where it belongs rather than just in the default geodatabase. And I'm going to call this contour underscore 20 and for 20 feet actually. And I always put the value in my, when I label my contours, just or when I name my contour data set, just so I remember what the interval is. So if I have to go to add it later, I remember exactly what it is. And then we put 20 in for the contour interval, and then we hit OK. When selecting your contour interval, it's really helpful if you take a look at this range that you have over here to select an interval. If it's a really close range, I would select a smaller interval. If it's a wider range, I would select a wider or a bigger value. And a lot of times I run contour multiple times to get exactly what I like, because sometimes I'm not sure what's going to look good or what's going to work, so I kind of play around with it. So with this one, my contour did not work. It's being a little fussy. Let's do that again. And that's actually, I'm kind of glad that that failed, just because you're going to have that happen to you as well. And so I'll show you some workarounds with that. So I'm going to select DEM, and then I'm going to, again, place it somewhere. I'm going to actually just take it up one level and put it in here. When you do rerun a tool, do not name it the same, do not name the output the same thing, and we talked about that with geoprocessing. Also, sometimes put it in a different location if it's being fussy. Sometimes it just doesn't like where you're putting it, like if your file path is too long or something along that line. So that would help. If this fails again for me, what I'm going to actually do is I'll shut down ArcMap and reopen it, because a lot of times if your tool keeps failing over and over and over, ArcMap is irritated, is what it means. So if you close it down, it cleans out the cache, and it usually solves the issue. And hit OK again. Cross my fingers, hope it works. It didn't work. So with that, I'm going to pause a second. Okay, so I restarted ArcMap because it was being a little bit cranky. So let's try to run this again, making sure that we put this in someplace we want it. I'm just going to call this again contour 20. Hit save, put my interval in, and hit OK. And you can see the tool running down here at the bottom. You can see the little globe spinning, which means ArcMap is working away. And usually when it runs this long, it means it's going to work, which is good to know. And you see that when it does work, you get a nice little green checkbox, and it automatically adds our contours to the map. Now, it adds them in a default color. I'm going to actually change the color to something else. And I'm going to zoom in to an area. And what's kind of neat is if you click on the contour, it will actually give you that particular contour interval. So that is 1640. Now, this is something that always gets students. Let's say that you want to label your contours. You right-click and you go to Label Features, right? Now, our contour interval was 20. How come these have wacky numbers that aren't a multiple of 20? The reason why is if we look at our attribute table, oops, sorry about that. If we look at our attribute table, we have two fields. We have an ID field and we have the contour interval field. What ArcGIS is doing, it's labeling the first field that it sees, so you have to go and make sure you change what a field is getting labeled. So so we go to our Labels tab, select Contour, and then hit OK. And voila, it's now labeling the right thing. So I just wanted to alert you to that when you do your assignment to make sure that you are labeling the right thing there. So that's how we generate contours. And again, we can generate them at any interval that we wish. Let's say you wanted to maybe do a bigger interval, let's say 50. And you can see that it added at the 50 interval, which might be a little bit better for this because it was a bit cluttered with using the contour interval of 20. And you can kind of see what it looks like. And again, I can label my contours using the contour field. And there we have our contours. So that's how to use the contour functionality in ArcGIS. Now let's go to do the Hillshade function. The Hillshade function is a shaded relief map, and this is actually probably the easiest one to do because you don't have to really do anything other than name your new file. So our input is always going to be the digital elevation model. I'm just going to call this Hillshade. And then the azimuth is essentially the angle of the light source. And this is kind of neat because you can play around with the azimuth and altitude to kind of show how a terrain would look at various times of day. So essentially what this Hillshade does, it basically is looking at shadows to help depict the landscape. So I'm going to hit OK here. And what it builds is a shaded relief map, and you can kind of see what that looks like. Now, the value in these that I think is really quite nice is if you put the DEM on top of the Hillshade, obviously you don't see the Hillshade anymore, but if you set a transparency then on the DEM, you get a nice little painted relief map out of it. So you would combine the digital elevation model with the hillshade to get that effect. So that's something that I really encourage you to do, is do that type of thing. But remember, you can this file here that we generated with the image analysis window is essentially the same thing. It's just that the colorings are just a little bit different. So it's really a matter of what you prefer in terms of your shaded relief map. So that's how you generate a hillshade map. Going back to our toolbox, the next one that we're going to do is slope. And again, slope is how flat or steep something is. So again, our input is always the DEM, because that's the thing that has the elevation values in it. We're going to name our data set appropriately, and I'm just going to call it slope because I'm uncreative right now. And then this is really crucial that you pay attention to this part here. You can pick what your output measurement is. You can pick degrees or percent rise, and it really doesn't matter which one you pick. It's really whatever your preference is. However, you have to put your unit of measure in your legend when you make a map of this. So you can't just say slope and then have your color scheme beneath that with the different elevation values. You have to say slope in degrees or a slope percent rise, or nobody's going to know how to interpret your map because they don't know what units your map is in. I'm going to keep mine in degrees, and I'm going to hit OK. And I'm going to turn off some of these other ones so we have the slope. So in looking at this, and let's just kind of go into this area up here, you can see that you have a map that ranges from a green color to a reddish color. The greener areas are areas that are more flat. The redder areas are the areas that are more steep. So you can kind of see where the flat and steep areas are on this particular area. Now, so again, just as a hint, when you go to make a map of this, some changes that you're going to want to make. First, you're going to want to change the name of your data set to be slope, and then in parentheses in degrees, so that the unit of measure is understood. The other thing that you would probably want to do is change the number of significant digits that you're seeing here. That's a little bit unruly and hard for a map user to really look at. So I would go to my format labels, and I would probably change the number of significant digits maybe to 4. Actually, maybe even 3, depending what you the level of detail that you want to go into. And then hit apply. That's just much easier to read and process than all of those digits after it. And again, if you remember from graduated color maps, you can go into click on the classify. You can actually go in and round off your break values if you wish to make it a little bit more readable for your audience. So that's a slope map. And looking at the name of the color scheme that's assigned to it, it's slope. So if you ever need to change that for any of your data sets, that's how you can find the appropriate legend for representing slope. So last, we will generate an aspect map, our data set. So again, our input is always the DEM, and our output, we will call it aspect. And hit OK. And while that's running, I'll turn this off. One of the beautiful things that Esri did in the latest, or 2 releases ago, I think it was, or it might have been the latest release, before when a tool was running, you kind of had to just sit and wait, and you couldn't actually do other work. Like you couldn't even turn a layer off like I just did. And they now have it where the tool processes in the background, and you can keep working on whatever it is that you need to do. So now this map that you're seeing, you're probably thinking, wow, that is really psychedelic and cool. And it kind of is. is also very interesting in terms of what it does. Aspect is showing us the direction of the slope. So like this red area, for instance, is a north facing slope. So anything that you see in red is a north facing slope. Anything you see in this blue color is a south facing slope. That's what this, how to use this map. And notice the legend that it brings along with it when you run the tool. It will, actually have the description of each, and then the actual value that's associated with degree values that are associated with that. And that's important because if we add this after the fact, let's say we add this, I went to the wrong folder there. Say that we add slope to the map after we run it. Notice that it adds it now all in black and white. It gives that black to white color scheme with it. What you can do again is, make sure that you select the slope color scheme that goes, or sorry, the aspect color scheme that goes with it to get that. And then if you want to kind of replicate this, you have to go in and actually go into your unique values area, and it's not letting me do that. You have to go into your unique value area to change that. So what I'm trying to express to you is make sure that once you run your aspect tool, make the map for the assignment immediately. Don't go and add it later. And I'm not sure why I added slope, but I added the wrong one there. Let me just do that again. I'm sorry. So we get that, and then notice that it's 1 to 360. If we go in here, change this to aspect, we get the aspect map that goes along with it. So with that, sorry to end in some confusion there. What you're going to be doing for this week's assignment is going to be very straightforward. You are going to be given a digital elevation model, and you are going to be asked to create contours, to create slope, to create aspect, and to create a painted relief map. So that's what you can expect, and you're going to find that this one will probably go a little bit quicker than some of the other assignments. So if you have any questions, please let me know, and I'll be happy to help.